Hello, dear students. Welcome back to my YouTube channel. I guess I am audible and visible to all of you. If yes, please let me know in the comment box. Hello, 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 hello. Yes, I am audible. My voice is okay. So, as you know, that today is our last lecture on magnetism, right? That includes magnetic effect of current plus magnetic properties. So today is our last lecture. So let us start the lecture. So in the previous class, we studied things about atomic magnetization, magnetic field at the center, magnetic movement due to orbital motion of electron. So these things we done in previous class. So now in this session, what we will be starting. So firstly, I will just write here lecture number 10. So this is lecture 10. Also last lecture. Last. Then look now. Look now. We are having two types of materials. Okay, about one material, one more material. Okay, look now. We are having one material in which in which each atom individual magnetic moment is zero. Individual magnetic moment is zero. Okay, important point. Each atom's individual magnetic moment is zero. So these substances are known as diamagnetic materials. Diamagnetic materials. If I need to show these things, if this is my representation of material, so these dots represent they doesn't possess any sort of magnetic movement. These materials are known as diatomic materials. Diamagnetic materials. Okay. So if each atom's magnetic moment is zero, so what about the net magnetic moment? So I can write net magnetic moment is also zero. Okay, these two things you need to just think about. It was also asked in the NEET examination, which among the following is not having magnetic moment, individual magnetic moment. So it is what? It will be a diamagnetic materials. So now we are having now second type of materials, so in which each atom possesses individual magnetic moment, known as paramagnetic or ferromagnetic. Ferromagnetic. So what is paramagnetic and ferromagnetic? Paramagnetic and ferromagnetic are those substances they possess individual magnetic moment. Let us suppose if I need to just make it now. Look now. They are having magnetic moment, but in a random motion. Random, no? It is random. It is not having any fixed now. If no fixed, so what you will write? You will write, sir, due to a random alignment due to random alignment net magnetic field equals to 0. So you can see now in both the materials, you can see, one second. Yeah. So basically in both the materials, whether we are talking about diamagnetic, para or ferromagnetic, in both the cases, net magnetic moment is 0. But if we look towards the individual particles, so diamagnetic materials, they doesn't possess, their individual atom doesn't possess any magnetic moment. But if we are talking about para and ferro, they do possess their magnetic moment, individual one, but net is 0 for both of them. Okay. Now let us understand. Now if we put these materials to external magnetic field, what will happen now? Okay. Second point is, if we are now going to throw them towards the external magnetic field, so you can write here behavior of magnetic material, behavior of magnetic material in external magnetic field. In external magnetic field. Okay. In external magnetic field. Okay, look now. Let us talk about diamagnetic. First about magnetic. Okay. So this ring shows it is a material made of diamagnetic material. Now here we are having a magnet, south pole and north pole. What will happen now? Okay. Now look, south and north pole, I guess my magnetic moment would be in this way. Yes, sir. Now if we talk about the lines, no, so my lines would be equals to it will go like this, no. These are my magnetic lines. Okay. Now here we are having a property. That we know, the Lenz's law. Okay. That is Lenz's law. We stated that this loop will get induced field. This loop will create an induced field. That induced field will try to push it back. That means it will oppose magnet. I guess it is only possible if this side would be north. So if this side would be north, so what you will write? Sir, you will write it is magnetic field of this loop will be in this way. Done? And current flow in this way. Very easy, no? Done? So, but what will happen here now? Look, this is my magnet initially. Initially, my magnet is like this. My magnet. This is my magnet with individual magnetic moment is 0. Now we are placing it to external magnetic field. B. What will happen now? This will get changed and it will oppose the magnetic field. So it will oppose. So it is magnetic moment will look like this now. Opposite means it will oppose, right? Oppose. Done? Hello, beta. So it will oppose it. But look, this property, na, this is opposition. So you will write this phenomena is weak repulsion. It is weak repulsion. Okay. It is weak repulsion. It is a weak repulsion. So you just need to remember one thing, that whenever our diamagnetic material is placed in the external electric field, it will oppose the external electric field. Then what will happen now? You can see north, it will repel this one, and this ring will repel your magnet. Okay. Navakirthana, better with this session, these are entirely sessions in English, right? So I need to just speak in English only. That's why. So this was all about the diamagnetic substances. Now let us talk about paramagnetic. Let us talk about paramagnetic. Second part. Paramagnetic. Paramagnetic materials. So these materials looks like this. Look now. Okay. 1 second. Look now. And I just told you in the beginning of this lecture, paramagnetic do possess individual magnetic movement, but in a random order, not any specific order, right? In a random orientation. Now, yes, beta, after completion of 12th standard, I will start 11th one. So now this particular figure represents paramagnetic material. Then, now if we place this material, expose this material to external magnetic field. Okay, this is my magnetic field external, and they do possess their magnetic moment. I guess we have one property known as torque. Torque is mb sine theta. mb sine theta. So what will happen now? With the help of torque, it will try to align. This torque will try to align these magnetic moment with magnetic field. With magnetic field. This is before, no? Before applying magnetic field. Before applying magnetic field. Okay. Now what will happen? What will happen now? After this, now? After this, what will happen now? Look. They will align, but not fully, not entirely. They try to align the magnetic moment in the direction of magnetic field. This one is after applying. You can write after applying magnetic field. Magnetic field. After applying, no worries, beta. Okay. So after applying magnetic field. So initially and finally. Bye, beta. Initially and finally. Look now. So you can see the direction of your magnetic field and direction of your magnetic moment in the same direction. So what you will write? Attraction or repulsion? Is this attraction or repulsion? This is attraction. Attraction, but weak attraction. Weak attraction. Okay. So diamagnetic materials, they oppose the magnetic field. So you were right there. According to the Lenz's law, they will oppose. So you were right, weak repulsion. But due to the torque in paramagnetic materials, there will be a torque, and torque tries to align with the magnetic field with the magnetic movement, due to which there will be a weak attraction. Okay, beta, thank you. There will be a weak attraction. There will be a weak attraction. Then number third. Number third is ferromagnetic. Number third is which one? Ferromagnetic. We are having ferromagnetic materials. Ferromagnetic materials, it looks like this now. Look. With some chambers or pockets. They're possessing something like this. It looks like this now. Okay. So these things known as pockets. These little things are pockets, and in this physics we are called them as domain. These are domain, and in this domain, hello Nikita beta, in this domain we are having our magnetic moment things, right? Look now, in a random orientation, no, in a random orientation, in a random orientation. Done in random orientation. It takes time now. I'm just making these diagrams, so it will take time. That's why I'm getting slow. Okay. This figure is before applying magnetic field. Now let us apply magnetic field now. Let us apply now magnetic field. But basically, these are materials. These are naturally occurring materials. Okay. This is my magnetic field B. Now, what will happen now? After applying my magnetic field, what will happen here? Look. One thing is there, no? Sir, these pockets are there. Yes, sir. These pockets are present. I'm not making 100% similar, no? There is no worries about it. No issue. Can make it like this. Okay. So there are two things. One is torque, and torque will try to align your magnetic moment with the magnetic field. Second thing is exchange coupling. There is exchange coupling. Exchange coupling means, let us suppose this one is coming in orientation with the magnetic field. It tries to bring second one. Second tries to bring third one. Third with fourth one. No? They are helping each other to align different magnetic movement with the magnetic field. This process is known as exchange coupling. This process is known as exchange coupling. In paramagnetic, only torque was there. But if we are talking about this thing, exchange coupling is also present. So there, look now, you can see magnetic moment direction and B direction is same. So there will be an attraction. There will be attraction, and this attraction is very strong. This attraction is very strong. Now, let us wrap up these three things. Dia, para, ferro. When we are placing dia in external magnetic field, the dia will oppose external magnetic field. Second one, when we are placing paramagnetic inside the magnetic field, it will attract, but that will be a weak attraction. Third one, if we are placing ferromagnetic, okay, it will strongly attract it. It will strongly attract it. Yes, today I am going to complete everything, na? Curie law also. Okay. Now I guess these things are done now. So we will start the different parameters that we will use in this chapter. Look now. I will write here different terms related to magnetism. So we are having couple of formulas and couple of terms that we are going to use in our magnetism chapter, right? Let us suppose we are having a loop, a solenoid like this. Okay, current I is flowing. So we know that now the magnetic field will look like this now. It will look like this. That means my magnetic field magnetic moment will be like this. We know it. And my magnetic field B naught will be equals to nu naught N I. We know it. Inside, if inside is air. We know it very well. Done. And what is nu naught? Permeability. What is n? Number of turns per unit length. I is current. Second term that we will use here, that is magnetic intensity. Second one is magnetic intensity. This thing is also known as magnetizing field. Magnetizing field. And we will show it with H. And its unit is ampere per meter. Ampere per meter. Basically, my magnetic field working and the magnetizing field working is same. Look now, you can just use these things now in place of one another. Magnetic field, magnetic intensity, both are same in different units, different domains. Okay, so you can write H. H is equals to B naught magnetic field divided by nu naught. What is B naught? It is nu naught Ni divided by nu naught. It came out to be, it is N times I. So my H magnetic intensity is Ni, and my B, it is nu naught Ni. And magnetic intensity, you can see magnetic intensity is independent on the medium, right? Because we don't have any here nu naught, no? Nu naught means it is depending on any medium. If there is no nu naught, so it is independent on the medium. So one term is magnetic intensity. Yes, it is nu naught, right? Magnetic intensity. So now let us do one thing. We are having a solenoid. This is my solenoid. Inside solenoid, current is flowing. Yes, sir. And we know one thing, that, sir, there will be a magnetic field in this way. No? These are my magnetic field in this particular way. So my magnetic moment will be in this way. We know this thing very well now. So this is south pole. This will act as the north pole. We know it very well. Now let us place a ferromagnetic substance here. This one, now let us place a ferromagnetic substance here. Let us suppose it is iron. This piece is iron. And iron is a ferromagnetic substance. Iron is a ferromagnetic substance. And we know that whenever we are placing a ferromagnetic substance within a magnetic field, it will try to attract. So if magnetic movement is in this way, so we will call one more thing, sir, that is iron's induced magnetic field will be also in the same way. Okay, that is iron's induced magnetic field will be in the same way, then only in this case it will be attraction. Okay, so look, if this is external, So if here is a ferromagnetic substance, so it is also having magnetic moment in the same way. So only there will be attraction. And why there should be attraction? We will just we had it no in the previous thing, right? Hello, beta. Now look now. Look now. So we will define a term known as intensity of magnetization. What is called as intensity of magnetization. Magnetization. That is up to what extent your this particular ferromagnetic material would get a magnetic properties, right? That means it is depending on current. Current is directly proportional to my magnetic intensity, that is H. So if we try to change this proportionality sign, so we are having a this symbol, chi symbol. This is CHI, right? And this thing is known as magnetic susceptibility. Okay, susceptibility. I don't know the pronunciation of it in a very good way. Okay, done. Okay, so basically now this what we're having here, look, this chi or magnetic susceptibility, it just because it shows you how easily a particular substance will get magnetized. This thing easily just tells you how a particular thing gets magnetized. Now look here, look here. If we are just dealing with this particular figure, so if you need to find out net magnetic field, if you want to write the net magnetic field, I guess, sir, one magnetic field is due to the external field. It is external, right? Due to current. One magnetic field which is inside and it is induced. How, sir? Look now. One is just because of this current. One is just because of this iron. So it is external plus iron. So look, B naught. Now here we don't have any ear. No, it is here we don't have any ear. No ear. We are having iron now. So I need to write nu naught, nu R, N I. External is nu naught H only, and B induced is nu naught I only. Okay, it is nu naught I only. Look now, what we can do right now? I can write nu naught. Look, I will just cancel out nu naught now. Look, nu naught, nu naught, nu naught cancel out. So what we are having now? We are left with nu R N I equals to H. What is H? So basically, H is Ni. So in this place, I will write here H. There is H plus I. But also I, we can write in the place of I, chi H. Yes, sir, I can write H. So can I write cancel out H, H, H now? Yes, sir. So my new R came out to be 1 plus chi. This is my ultimate formula that you need to remember. This is my ultimate formula that you need to remember. Done? Okay. Okay, now we will one more property is there, that is magnetic or magnetizing current. Magnetizing current, that is IM. Look better. Simple case. If we are having a loop or a solenoid like this, okay, current I is flowing and I will leave. And I will leave. Done? So I know it is magnetic field is nu naught and I, we know it. Let us increase, let us place a magnet here. After placing this material, it is iron material. So what will be there? Sir, B will be equals to nu naught nu R n times I. That means B increases. It increases. Now I want to increase the magnetic field. I want to increase the magnetic field just like this, but without inserting any ferromaterial. I don't need to insert any ferromaterial. I want to increase the magnetic moment. Sorry, magnetic material. Okay. Look, here we are having a coil. So current is flowing through this loop. Okay. So my magnetic field is like this. I increased its magnetic field by increasing a dielectric medium, by increasing a ferromaterial. Yes, sir. So my answer came out to like this. So I want to increase, na? I want to increase, but I don't want to put any ferromagnet inside. So what I will do, I will just increase the current, and that current increase means it is a magnetizing current. So now my B came out to be nu naught, same as a nu naught, and same, we are having current is I plus Im. So this Im means it is magnetizing current known as Im. Very simple and very easy. Very simple and very easy. Okay. Okay. So let us do a numerical. Let us do a numerical. And numerical like if we are having a loop with 1000 turns per meter, 1000 turns per meter. And if current I is 2 ampere, nu R, it is 400. First thing, find H. Second thing, find I. Third thing, find B. Fourth thing is chi. Fifth thing, Im. How to find these all things? Basically, it is an NCERT problem, right? It is an NCERT problem. This is a NCERT problem. First thing, how to find H? Sir, we know H is nothing. It is N times I. And N is 1000. I is 2. So my answer came out to be 2000. 2000 ampere per meter. It is 2000 ampere per meter. Done. Now B. B is I. What is I? Sir, I is chi H. Chi we don't know. So for chi we are having one more thing now. So we will write nu R. Nu R is equals to 1 plus chi M. Nu R is how much? It is 400. 400 minus 1 came out to be chi M. That is chi came out to be 399. I guess fourth option now. It is done. Fourth option now. Yes, sir. It is also done. Okay. Now I chi is 399 into H is 2000. It is approximately, I will take 400 into 2000. So it came out to be 4 to the 8. It is 835 in 10 to the power 5. Done? I beta 10 to the power 5. And unit is ampere per meter. Okay. So now H is done, I is done, this is done. Now we have to find out B. It is third part. C is B, right? So what is B now? B is nu naught, nu R, n times I. Nu naught is 4 pi into 10 to the power minus 7. Nu R is 400. N is 1000. I is 2. So look, 70250. It is 40. So I guess my answer came out to be 4, 3, 12, 12, 2, 12, 4 to the 8, 12, 8. I guess it came out to be, look, I will write in just 4 into 3.14, 10 to power minus 7, 3 plus 5, it is 50 into 2, right? It will be 4 to 12, 12 to 24. 1 second. Look, no, 4 for 16, it is 4 also. 4 to the 8, 24. 1 second. Look, 4 into 4, 16, 16 into 32. It is 32 multiplied by 3.14 in 10 to power minus 2. So I can write it equals to 100. I can write 100 10 to power minus 2. So it is 1 only, no? It is 1 Tesla. It is approximate value, no? You can write it. There is no issue. Okay. You can write it, no? This thing is done. Now we are having this current. Fifth part is current. Okay. So I guess B equals to nu naught N I plus Im. So I need to find out what? Im, right? Yes. So Im is equals to B divided by nu naught N minus I. B came out to be 1. Nu naught is 4 pi 10 to power minus 7. N is 1000 10 to power 3 minus I. I is how much? 2, right? Okay. So I can write minus 7, 3, 4. It is 10 to the power 4 divided by 4 into 3.14 minus 2. So it is 11040 divided by 4, 12, something 14, no? Something 14. Okay. Done. So it comes out to be 14 to 5, 0. Somehow 795 amperes, something like this, no? It will come something like this now. Okay. Now look, one more thing. Very important. If we are placing diamagnetic, right? Diamagnetic. So in diamagnetic, what we are observing? We are observing weak repulsion. We are observing weak repulsion. Weak repulsion. Weak repulsion. Right? So look now, if this is my material, okay, my material, and external field will looks like this now. Why, sir? Because this magnet now, this magnet is repelling now. This is repelling little bit, but still it is repelling. So now if external is B naught, internal is B, so what you will write? Can you write B naught is more than B? I can write it. What is B naught? Is it nu naught Ni? More than, is it nu naught R nu naught Ni? Cancel out. So therefore you can write here, therefore nu R is less than 1. If nu R is less than Y, so what do you know? I get nu R equals to 1 plus chi, right? So look now. So what is chi m? Is it nu R minus 1? Okay. So this thing is also less than 1. This thing is also less than 1. Suppose, for example, suppose nu R is less than 1. That means it is simply 0. Let's suppose 2. So what will be chi m now? Sir, 0.2 minus 1. Okay. So chi m came out to be, it is a minus 0.8. Then now, so for diamagnetic substances, nu R is less than 1 and my chi is negative. Is a negative. Or you can write it is less than 0. Okay. So from this topic, you will find these numericals in your PYQs. Okay. Second, if we are dealing with paramagnetic, substances, paramagnetic. So paramagnetic still, if this is my material, okay, so there is a weak attraction. Weak attraction. Still, if it is a weak attraction, so you will write. What you will write, sir? You will write, look now, look. External is B naught. Here we are having B, and B is more than B naught. Why? Because there is a induced magnetic field also. So you will write internal is more than external. What is internal? Is it nu R, nu naught, Ni? Is it more than nu naught Ni? Cancel out. So nu R is more than 1 for my paramagnetic substances. So nu R is equals to 1 plus chi m. More than 1 minute, it is very, very big, right? So can I write here? Can I write here now? Chi m came out to be nu R minus 1. So it is very big. So I can write chi m is equal to, let us suppose it is 600 minus 1. Suppose, not suppose, example. So chi m came out to be 599, which is very big, right? So basically, if we talk about reality or experimental data for these things. So my nu R is more than 0, or if we talk about 1 and less than 2. Okay. And my chi m, it is less than 1, more than 0. That means it is positive. This one is also positive. This one is also positive. Both are positive. I'm just stuck now. 1 second, I need to check it out. Why my failure stuck? 1 second. Okay, so Sam Boom. Hello, beta. Okay, so I guess we are done with diamagnetic and paramagnetic. So let us start. First of all, I need to check my network connectivity. Then we'll start. Okay, so we are having now ferromagnetic. So in ferromagnetic, my internal is very more than my external. Internal means nu r, nu naught, ni. It is more than nu naught, ni. Cancel out. So my nu r is very greater than my I. Sorry, my 1. Okay. One more thing. What is nu r? Nu r equals to nu divided by nu naught. If this thing is very more than the 1, so I can write my nu is more than my nu naught. Okay. And what about the chi, right? So nu r equals to 1 plus chi m. I can write chi m equals to nu r minus 1. This particular thing is very more than the 1. It is, let us suppose, 800. Okay, so my chi m came out to be more than 1. So these things you need to remember from this particular topic. Done? So give me 5 minutes, then this lecture is over. Look now. But still we are having some materials known as superconductors. We are having some materials known as superconductors. Superconductors. Sir, what are these superconductors? So let us suppose this is my superconductor. If we are placing any external magnetic field, B naught, so this particular material will repel 100%, 100% repulsion, 100% repulsion. Okay. So what is B inside? Sir, B inside of my superconductor is 0. B inside means it is nu r nu naught ni equals to 0. So you can check out my current cannot be 0. Number of turns cannot be 0. Nu naught cannot be 0. So only one thing, that means nu r came out to be 0. For superconductors, nu r is 0. What about chi m? So nu r is equals to 1 plus chi m. Nu r is 0. So chi m came out to be 0 minus 1. That means chi m came out to be minus 1. One more thing, if my chi m is equals to 0, this particular thing means it is non-magnetic substance. Non-magnetic substance. And this whole phenomena is known as Massenert effect, dedicated on the name of scientist. Massenert effect. Okay. Okay. One more thing. This is experimental data. Experimental data. Experimental data. That is, if we are talking about diamagnetic substances, these are repulsed materials. So we found that it is chi m. We know that it is negative, one thing, but it is temperature independent. Temperature independent. That means if we are talking about, one second. Temperature terms. So my property of my material, it is negative, but it is independent on material. So the line will show like this. Now, if we are talking about paramagnetic, substances. So per paramagnetic substance, it is experimentally proved that my XM magnetic susceptibility, it is inversely proportional to my temperature. That means if you are increasing the temperature, the magnetic properties decreases. So I guess it is inversely proportional graph. So it will be looks like the rectangular hyperbola. Look now. If my material is like this and magnetic moment is like this, right? If you are increasing the temperature, order gets disturbed. If the order gets disturbed, so magnetic properties get disturbed, right? That's why if you're increasing the temperature, xm what decreases. It is inversely proportional graph. Clear? So for that, we are having a very important relation. This chi m is equals to c by t from this law, and this law is Curie law. Marie Curie gives this law. That's why it's known as Curie law. Curie law. Now, if we are talking about ferromagnetic, if you are talking about ferromagnetic materials, as you know that the ferromagnetic materials possess some small pockets known as domains. Okay, so as we increase, look, as we going to increase the temperature, the alignment of my magnetic moment gets changed. There will be a temperature. If we increase the temperature from that standard temperature, ferromagnetic gets changed to my paramagnetic. That particular temperature is Curie temperature. Okay, so you will write above Curie temperature. Above Curie temperature, my ferromagnetic changes to paramagnetic. My ferro changes to my paramagnetic. That means chi m is inversely proportional 1 divided by T minus Tc. Tc means Curie temperature. Or you can write this law as chi equals to C naught divided by T minus Tc. Done? It is Curie-West law. This is Curie-West law. Done? Now the last topic of our chapter is frog levitation, and you will find this topic in your NCERT known as frog levitation. First thing that you need to know that if we are talking about animal tissues, these animal tissues, they are possessing a property of diamagnetic materials. Diamagnetic. That means simply indicates they will repel. They will repel a magnetic field. If we are having a something like this, clear? Current will flow through this. And we are having a magnetic field like this. Here we are having a particle with mass m. Due to gravity, it will fall down. But as you know that it is what? A diamagnetic. It is what? A diamagnetic, right? So there will be a repulsion. This force will repel it. So it will hang. It will hang. It will hang. Okay. So with this topic, we completed the topic. Okay, we complete. What did we complete? Magnetic effect of current. Magnetic effect of current with magnetism. So these two topics we conclude. Okay. Now from tomorrow we will start EMI. From tomorrow onwards we will start EMI. EMI. Electromagnetic induction. I hope you enjoyed this session, and if you have any doubts or anything like that, you're most welcome. You are having my Telegram ID link, right? So you can just 1 second. It is not any visible now. I guess some camera issue now. blurry face, right? Yes, I don't know what happens with my camera. So no worries. So I will take the leave now. Thank you, Beta. Thank you very much for the session. Thank you. Bye. Bye. Good night.